Hello, I am Timothy Kuo from Penn State University. Now, I'm excited to introduce my research with Dr. Hui Yang titled Federated Learning on Distributed and Encrypted Data for Smart Manufacturing, and is published in Journal of Computing and Information Science in Engineering. This groundbreaking work explores how federated learning, applied to encrypted data, can significantly enhance data privacy and facilitate collaborative machine learning in the realm of smart manufacturing. For those interested in delving deeper, I invite you to explore the comprehensive details in my paper. In the last decade, we've seen the development and deployment of Industry 4.0 technologies. A report from the International Data Corporation highlights this surge, noting that the manufacturing sector alone generated a staggering 3,584 exabytes of data in 2018. This figure is projected to skyrocket to around 22.5 zettabytes by 2025. This vast amount of data is often distributed across various business units among cooperative companies. However, such distributed data-rich environments significantly heighten the risks of cyber attacks, privacy breaches, and security violations. Alarmingly, it's reported that over 90% of organizations in sectors like manufacturing, healthcare, and transportation have suffered at least one major cyber attack in the last 2 years. Traditionally, data from different business units are collected and centralized for the development of machine learning models. However, data ownerships are segregated, with each unit maintaining distinct levels of privacy governed by individual data management policies. Consequently, many stakeholders are hesitant or outright refuse to share raw data for centralized machine learning due to privacy concerns. Therefore, our paper presents a novel privacy-preserving framework to enable federated learning on siloed and encrypted data for smart manufacturing so that we can reduce the likelihood of data breaches while maintaining the prediction performance of machine learning models. In this framework, we design 3 layers of protection mechanisms, namely segregated data ownership, data encryption, and federated learning. In the Layer 1 protection of our framework, which centers on segregated data ownership, we have designed a framework where raw and unencrypted data are exclusively owned by their owner. This approach establishes a distinct privacy boundary between different factories. In essence, each factory has access to and ownership of only its own data. This ensures that the data privacy of each entity is respected and maintained, creating a secure environment where privacy is protected. In the second layer of protection, our framework employs fully homomorphic encryption to protect data privacy. This advanced encryption technique allows for computations to be performed directly on encrypted data. The remarkable aspect of FHE is that it yields encrypted results which, when decrypted, are identical to the outcomes that would have been obtained if the same operations had been conducted on the original, unencrypted data. This capability is crucial as it enables secure data processing without ever exposing the raw data. Thus, FHE not only protects the data at rest, but also ensures its confidentiality during computation, bridging a critical gap in data security practices. In the third layer of protection, our framework departs from the traditional centralized learning approach, adopting federated learning for the development of machine learning models. Federated learning allows each data owner to develop and refine machine learning models using only their own data. This process ensures that sensitive data remains within the confines of its original domain, significantly reducing privacy and security risks. The key innovation here is that while the development is decentralized, the insights gained are collaboratively amalgamated. This is achieved by aggregating the learnings from each independent model into a comprehensive consensus model. Such a strategy ensures that collective intelligence is harnessed without compromising individual data privacy. In recent decades, society and the natural ecosystem have experienced significant impacts due to climate change. The aim to mitigate these impacts involves limiting global carbon dioxide. Mitigating carbon dioxide is especially challenging, mainly due to its strong connection with energy generation and consumption processes. Both carbon emission and climate change have driven a growing emphasis on devising strategies to optimize energy consumption, monitoring, and scheduling. Therefore, a prediction model of energy consumption is urgently needed. In this case study, 5 distinct facilities, designated as Factories 1 to 5, possess independent ownership and control over their respective datasets. If they collaboratively work towards the development of a prediction model for energy management, the concern of data privacy emerges. We first do experiments to identify the useful features and the optimal prediction model of this case study. After that, we evaluates and validates data encryption and computational operations of FHE method with regard to their influence on prediction performance. This study builds two distinct prediction models, including the modal integrating FHE mechanism and the modal without encryption mechanism. As you can see, the difference between encrypted and non-encrypted models is minor. Therefore, the proposed privacy-preserving framework does not lead to a reduction in the prediction performance, while the encryption mechanism is adopted to protect data. We then conduct a performance comparison among FHE with the federated learning model and independent models for factories 1 to 5. As you can see, among these four performance metrics, FHE with the federated learning model achieves superior prediction performance. Last, when we look at the protection of data privacy, we found that the proposed privacy-preserving framework overcomes the catastrophic consequences of data breaches, even if a hacker successfully attacks the database. First, when there is a data breach in Layer 1 protection for one factory, only the raw data of that specific factory is exposed. Data belonging to other factories remains protected due to segregated data ownership. Second, a hacker can only access encrypted data in Layer 2 protection. In other words, without the correct pair of keys, hackers cannot decipher the real data from its encrypted form. Last, if data are exposed in Layer 3 protection, an attacker can only obtain encrypted data and parameters of machine learning models from one factory, because the model development is distributed. Therefore, the proposed framework mitigates the risk of data breaches when multiple independent data owners collaborate in developing a machine learning model. In conclusion, the proposed framework shows strong potential to promote smart manufacturing while preserving data privacy. This paper is supported by the U.S. National Science Foundation. Thank you.